Thank you for being here. We are going to be covering session 7 and 8 today. So we'll go ahead and we'll get started with number 7, which is called Normal Loading 1, and session 8 will be really originally named Normal Loading 2. Okay. So in the last session that you most likely watched as a video, we were discussing material properties, and we'll have a brief recap and a little bit of errata that I made when I recorded that. And then we'll go into volumetric strain and dilation, or dilatation, bulk modulus, and distributed axial loading. Okay. As I think you said you had a question on one of the problems from the previous assignment, so if we could wait till a little bit later to get to that, is that okay?
Yeah.
We'll do that. Are there any administrative questions at this point? Okay, all right. So exam is a week from yesterday, so it'll be on Tuesday, and you can bring a handwritten sheet of notes with anything you want on it, okay? So last time we had the opportunity to discuss different material models: linear elastic perfectly plastic model, the linear elastic linearly plastic strain hardening model, and we introduced some terms or some characteristics of materials, their resilience, their toughness, and the Poisson's ratio. And of those three, the one that we'll see come up more in the course is the Poisson's ratio. I mean, these two are very important. The Poisson's ratio ends up affecting how we look at strain. And as we look at 2.5D problems, as you've already seen, it affects the amount of contraction or expansion we have in a member as it's axially loaded. And we can also talk, or we did talk about general approach to solving problems in mechanics, and this is based on Crandall Don Lardner's book, and it has to do with breaking things down into equilibrium, into geometric compatibility, and then a set of constitutive equations, which are relating the deformation and the forces, or the moments, or the loads to each other, or the stresses. So just a couple things. If you watched the video, we talked about the Princess Bride, and I made a mistake about what type of machine they had in the Princess Bride. It's not a stretching machine. It's something that sucks the life out of a person. Apologies for making that mistake. And there was also some issue with example 6.5, and that's been corrected on the slides. And thank you to Michael, Mark, and maybe some others who looked at question number 6. Actually, there was an issue with it last semester, and then I made another issue, I think, yesterday. So anyway, it should be resolved. The result is supposed to be in nanometers. And thank you for using the GroupMe. Okay, so let's go ahead. Normal loading, session 7. And we're going to first discuss volumetric strain and dilatation and bulk modulus. So if we start with a box, which we can think of as either a material element or an infinitesimally small portion of a structure that we're analyzing, we can describe its volume. And we can put some dimensions on this box as well. So this is a really small box with lengths of dx, dy, and dz. And we have a coordinate system as well. If we apply normal stresses to this box, sigma x, sigma y, and sigma z, it will change its volume and potentially change its shape as well. So if these stresses were compressive, we would see the box getting smaller, right? And in this case, what we're seeing here is that this was the original kind of idea of what the box's dimensions were. And then as we've applied what seem to be tensile stresses, 6 sigma x, sigma y, sigma z, this box has expanded and its volume is now larger. So we have a new volume, V naught plus delta V. And if we begin to think of the change in lengths of these sides of the boxes, okay, we can think of them in terms of some type of strain, okay, times the original length. So strain, right, is typically a number less than, much less than 1, right? We're talking, less than 0.1%. So if we say 1 plus that amount of strain that we have, and we multiply it by the original length, we can get the new length of that side of the box, right? And we can also look back at kind of the original definitions of it, what strain is. At least engineering strain, as we defined it. So a new volume, okay, V naught plus delta V, right, can be thought of as being the product of all these new lengths. Okay, so we can write it out as you see here. And if we go a little bit further and we just think about what is this change in volume, okay, this delta V, all right, we can say, oh, we're going to take this new quantity that we have for V naught plus delta V and subtract away the original V naught, okay, and this is going to be the change in volume that we have. Right? And then we do a little bit of algebra and we make use of some approximations. So, for example, right, if you use FOIL multiple times on this, for example, right, first, outer, inner, last, you do some algebra, right, you'd see, oh, okay, well, I'm going to have a 1, right, because I have 1 times 1 times 1, and that would give me like a 1 dx dy dz, and I have a minus 1 dx dy dz, so that goes away. But then you also see things like, well, I would also have like epsilon x, epsilon y, epsilon z times each other. Well, those are 3 very small things multiplied against each other, and so those will also disappear. And even if you have like an epsilon x times an epsilon y, that's going to be much smaller than, say, just like an epsilon x. So what you end up getting if you do it out is this approximation where epsilon x, epsilon y, epsilon z, they dominate and they add to each other, and you multiply it times the original volume. Now, dilatation is a metric that we can use to think about how the original volume, V naught, the original volume here, okay, how that relates to the change in volume, right? So this is the change in volume right here, and this is the original volume right there. And so here we can say, okay, just taking this term that we have for the change in volume, right, this delta V, epsilon, this quantity right here, epsilon x plus epsilon y plus epsilon z, times that, and then divide by the original volume. And what do we get? We get epsilon x plus epsilon y plus epsilon z. Okay. And we have some idea of what epsilon x, epsilon y, and epsilon z are for a volumetric element, right? So when we talked about the Poisson ratio in session 6, we discussed how a stress in a given direction, right, can still be related to a strain in that given direction. But if there are stresses in orthogonal directions, so like in the y and z, so like, we're thinking about epsilon x. If there are stresses in the orthogonal directions, they don't change the stress in the sigma x direction, okay? But they do affect the strain in the epsilon, in the x direction, right? If I've got, how do we put this multiple ways, but if I've got a bar, right, and I'm just applying the stress sigma x along that bar, right, assuming that the x direction is in the length direction of the bar, then we can say, oh, well, the strain is just this 1 over e times that stress. But if I have now stresses in the orthogonal directions, right, and I'm pulling it in tension in those two other directions, I'm going to be thinking about how the strain in that x direction actually goes down, right, because I'm pulling it apart in these other directions, so it's going to want to go this way. Okay? And that's true for the y and the z directions. So another way of writing out the dilatation is to think about this epsilon x, epsilon y, and epsilon z in terms of the associated stresses in x, y, and z. So relating them through, so essentially substituting these in there gives us this expression for the dilatation. Now, this is exactly what we described previously, and another way to think about the dilatation is as a volumetric strain, right? Because a linear strain is what is the change in that length divided by the original length. A volumetric strain is what is the change in volume divided by the original volume. And we just wrote that this dilatation can be written as an expression in terms of the stresses, instead of epsilon x plus epsilon y plus epsilon z, right? So that's, there are two forms, right? There's this is also epsilon x plus epsilon y plus epsilon z. Okay. Now, how do we think about this? If we go back to this volume box, right? We just thought about it in terms of it being this volumetric box, this nice little infinitesimally small cube. We are thinking about what happens when we pull it apart with a sigma x, sigma y, sigma z. Okay. Now what we're going to think about, okay, is what's called hydrostatic loading. Any idea? Has anyone heard of hydrostatic loading? Any ideas? What is hydrostatic loading? What is it? What does it make you think of? You're thinking. I see the wheels turning there.
Well, hydro, so like water?
Yeah, right. So hydro, right? Water. Okay. What happens if you drop a rock or a cube into water, Jason?
The water ripples.
Good, right? The water ripples. So that's a dynamics problem. Okay. Now let's go back to statics. Let's say that we've got that cube or that rock underwater. Okay,
There's pressure on it?
Yeah, there's pressure, right? And for our intents and purposes, if this block is underwater at some depth, it has equal pressure acting on all sides. Is this, maybe you did this at some point when you're studying buoyancy in physics? Okay, so in hydrostatic loading, okay, what we're saying is that there are going to be these pressures acting inward, okay, compressing the object. Okay, so now our stresses that are acting on the object are in this negative sigma x, negative sigma y, and negative sigma z directions. Okay, so if we go back to what is dilatation in terms of pressure, we can write it as the following, okay? Right? We had sigma x, sigma y, sigma z being added to each other. We have now negative p's for each of these, so these become the negative 3 p's, okay? And so now we're thinking about this volumetric strain, okay, in terms of the pressure, okay? underwater, or maybe it's in a chamber, right? Maybe you've got anyone used an air compressor before, right? So maybe you put your object in the air compressor, and then so now it's being compressed by that pressure. And we will talk about pressure vessels, which is a slightly different thing, soonish in this class. But we're just talking right now about this object that's being pressurized. So now what we can do is introduce something that's called the bulk modulus. So the bulk modulus is something that you'll see reported, okay, as a material property, and gives us some type of idea of how a hunk of material, a chunk of material, all right, is going to respond to a pressurized environment, to hydrostatic pressure, okay? So this, you can think of it as, and it's K, which is a little bit confusing considering that we've been using K for our spring coefficients and spring constants, all right? But K is a commonly used variable for the bulk modulus. And we can see that if we know the K and we know the pressure that's being applied, we can figure out what the volumetric strain or the dilatation would be. And look at this. This expression, okay, and this expression, okay, we have this interesting, we can manipulate things here, right? So we said that dilatation in terms of pressure is this little e over minus 3p over the elastic modulus times quantity 1 minus 2 nu. Well, we can manipulate things, all right, a little bit here. And what we see is that this bulk modulus is related to the elastic modulus and the Poisson ratio. Okay? So you can go from properties that are reported for tensile testing on a material to a bulk modulus, which gives us some idea of how this material is going to respond under pressure, okay? Under hydrostatic loading. So, right, and so you see this is V naught over delta V, right? So you move this to this side, and then you've got this quantity, okay, right here, and there's a negative, right? So it just comes out directly from here. This is something that you might want to just write on your sheet, okay, for exam 1, and yes, it gives us an ability to relate the volumetric strain to pressure, okay, as you see here. So if we have a pressure, and it looks, right, this looks remarkably similar to what we've talked about in terms of sigma equals E epsilon, right, where you have elastic modulus, or it looks, like F equals K delta. The bulk modulus is going to have units of stress, okay, or pressure. Once again, just like strain, right, the dilatation, okay, or the volumetric strain is going to be dimensionless. It's not going to have dimensions. So, and we're relating it to a pressure. So that means that the bulk modulus itself is going to have units of pressure. And we talked about that a little bit yesterday, actually, when we met. And it may be in units of gigapascals. Okay. Another interesting thing is that if the Poisson ratio, right, is 0.5, okay, then this bulk modulus will shoot up to infinity, right? So most of the materials that we're dealing with in this class, they have a Poisson ratio of around 0.3, okay, or somewhere, 0.33, 0.23, something in that ballpark. But the rubbery materials, they actually have a bulk modulus, Poisson ratio of approximately 0.5. And for numerical simulations and various other things, we usually use something like 0.48 or 0.49 for that value. But it's just something to note that can be a problem. Okay, So what are some examples of bulk moduli? All right, so here's a little table that actually I created, and you can recreate if you want using Colab, using Python. And here's the code if you like it. But we're probably, and to be honest, I'll be completely honest, I am pretty good at remembering these two and maybe these three values, right? Because Poisson ratio is typically 0.3 for the metals we're dealing with, so I'll just use 0.3. And aluminum and steel, I do hope that those values you do memorize for this class, the elastic modulus, okay? But if you go around and you ask people, hey, what's the bulk moduli for aluminum and steel? They're not going to be able to like rip it off the top of their head. Okay. Now, I mean, maybe if they work in this area, they will, but that's not something that I'd be able to memorize, right? But if you have this on your sheet, you could calculate it out. And if you have it on your sheet, right, you can use the equations, right? You want to have this P equals minus KE. You want to have what K is here, and you want to have dilatation and the volumetric strain. So you'll be set. Okay. But the other thing, I guess this maybe I've emphasized this previously in person with people, and also in I think in the videos, is that more or less a rough approximation for elastic moduli are for steel and aluminum is that steel has an elastic modulus about 3 times that of aluminum. So if you remember aluminum, or you remember steel, and you remember the factor 3, you should be good to go. And it's interesting that, at least for aluminum, the elastic modulus and the bulk modulus are actually pretty similar, okay, between those two. And, it doesn't change a whole lot for steel either. But like we were saying, right, with silicone rubbers, right, they get very close to having a Poisson ratio of 0.5. And so that means that they get a serious boost, even though the elastic modulus of silicone rubber is very low because of its Poisson ratio close to 0.5. It shoots up the bulk modulus quite a bit. All right, and what does that mean? What does a high bulk modulus really mean? Okay, that means that if I have pressure and I have a high bulk modulus, this means that the amount of volumetric strain that I get is not that high. Okay, that's what it means, right? Because I can do minus P over K is equal to E, and so it's maybe a little counterintuitive that because a rubbery material has a high Poisson ratio, okay, then it has a pretty high bulk modulus as well, much higher than its elastic modulus. Yes?
Well, things like Q's, is there a change in each direction, or does it start to like a sphere?
Okay. Well, that's a good question. So we're going to be assuming like it for this situation, it's a pretty good assumption underwater. Because the stress is the same on all sides, it's going to stay more or less a cube. Okay. Yes, but you could think that's an interesting question, because I think people, if you're an animator, right, you've got some type of object going underwater, you might be tempted to shift its shape as it gets deep under the ocean. Okay, and with a pressure vessel, that's going to be true, right? Things are going to collapse eventually underwater. Okay, but that's kind of a hollow structure, right? We're talking a solid structure. But I had to think about that. Would it? There's our simplistic perspective, and there's the reality. I would still lean toward it not changing that much into a sphere, okay? But I could think about that a little bit more. It's an interesting question. Okay, so Now, here's an example. We drop a block made of aluminum with each side having a length of 1 meter. Okay, that's a pretty big block. Okay, that's a pretty big block. And that we pressurize up to 100 atmospheres. Okay. What is the change of the volume of the cube, and what is the change of length of one side of the cube? Okay, and what would be the equivalent depth underwater to get to 100 atmospheres of pressure? So we can make our nice little cube. It's my cube, so it's a little distorted. And we have this pressure, and we want to know the following 3 things. We want to know what is the change in volume, we want to know what is the change in length, and we want to know how deep. Okay, H is how far underwater would be equivalent to getting to 100 atmospheres. So aluminum from the previous slide has a bulk modulus of close to 70 gigapascals, which is close to its elastic modulus, which we just discussed. We're applying pressure, the same amount on all sides. And maybe we'll go ahead and use the CDO approach of breaking it down into equilibrium, geometry, and constitutive equations. You don't necessarily have to do that, but we have balanced forces, and this thing is going to be in equilibrium because the pressure is acting on all sides. In terms of the geometry, we have a cube, and we expect it to contract. We expect it to get smaller. And in terms of constitutive equations, well, we know what dilatation is, and we know that we have a relationship between pressure, bulk modulus, and the volumetric strain. Right? Dilatation being the volumetric strain. So now we can say, all right, well, the change in volume is just going to be rearranging this equation here. We can say that we now have our E times V naught, and so we can use this equation, right, for E, we get minus P V naught over K. We can say that the volumetric strain can be given by epsilon x plus epsilon y plus epsilon z. Okay, so we've already solved for the delta V. Okay, if we want to look at these strains being the same, okay, and that's a fair assumption because they are all related to sigma x, sigma y, sigma z being P. So we can say that the epsilon x is equal to E over 3. And if we want to look at the change in length, we can go back to the definition of linear strain, and we say that it's L naught times epsilon x. Okay, and this one, I don't know, I guess this one might be a little bit, is this familiar? Is this equation? This comes out of was this familiar? Do you guys remember hearing rho GH is equal to the pressure underwater? Maybe? Okay, so, it is. All right, we won't derive it here. Okay, but if you go back to like some of the physics and some of the stuff you learn on buoyancy, okay, you can figure out that the pressure at a given depth is going to be equal to the density of that material or that liquid surrounding times G times the change in height, right? And there's an expression for the depth. If we plug in some numbers, what do we get? And this is using Python, right? So we can say, okay, we're plugging all this stuff in here, and in the end, what do we get? We get that there's a change of volume, okay, of something in centimeters cubed. Another way to write centimeters cubed is millimeters, or not millimeters, milliliters, all right? We can say that there's a change in length of about 49 microns in a given direction. And we can say that this is equivalent to going down 1,000 meters. So a rough approximation, if you're interested, you go down 10 meters and you've got one more atmosphere acting on you underwater. Okay? That's pretty significant, actually. Okay, and if any of you, dive down to the bottom of the Wurblin pool, okay, you know that your ears are going to feel something. I had that unexpected opportunity not too long ago. I was actually paddling with a surfboard in Wurblin, and I tried to remember to take off my ring, but this time I didn't. And this was a kind of, I wasn't convinced that it would ever really come off, okay? But I was paddling, and it came off, and it went down to the bottom. And I had to get some goggles, because I was paddling on a surfboard. I was just working out. And so I had to go and ask them for goggles, because I couldn't see. And I was really concerned. It was in a part of the pool that is not the I don't know if you've gone swimming in the lanes. Has anyone gone swimming in Wurblin? No? Yes?
Yeah.
Okay, right. So you know that as you're walking out of the lockers and you look on the left, right, it's pretty shallow usually because they have them set up for 25 meters most of the time. So I was on the right, and it was deeper, and it was in that it goes off there's a pretty good slope to the bottom of the pool, and I was nervous that I was gonna not find my ring, but fortunately within a few minutes I went down and I was able to get it. But that's right, that is probably it's probably about probably about a meter, or actually it's probably about 3 meters, okay, because it was probably around 10 feet. And so that would have been like a third of an atmosphere.
Is that just from pressing your finger so the ring slipped off?
Oh no, the ring slipped off while I was that was a dynamics problem. So I was paddling, okay, and the ring slipped off my finger just from it being a little bit loose. Yeah. Okay. And yes.
When you did 3 epsilon x, because all strains on each side are equivalent because it's water.
Yeah.
Are you able to do that because it's a cube, or if it was a rectangle, you could still do it?
You would still be able to do it, okay? If it were not, you want it to be some type of rectangular object,
Yeah.
right? Because we have epsilon x, epsilon y, epsilon z. If it's so that makes it easier for us to do this, okay? And this is strain, right? So it's it's not saying that the change in length, like if you had a rectangular object where the sides were not the same, right? Then you would expect that there could be some change in the lengths, right?
Yeah.
Of contraction if you have an object that's not a cube. Okay, good observation. Thank you, Owen. Yes.
Do we convert ATM to units per meter squared?
Okay, so yeah. So you can, right? So 1 atmosphere, all right, is about the same as 1 bar, but 1 atmosphere is 101.3 kilopascals. Okay, so it's about 100 kilopascals is 1 atmosphere. So yes, it would have units of force per length squared. Okay, it's a pressure.
Is the SI unit Pascal still?
Yeah. So atmosphere, so SI is it's fine to use pascals, right? And as you know, right by now that we're looking at, 100 kilopascals, right, is about 10 to the 5th pascals. Now we tack on another 2 zeros, right? So that gives us 10 to the 7th pascals. So this is really 10 megapascals of pressure that we're talking about. Okay. Good. All right, so the first assignment question is related to this, and I won't do it here, but you'll have the opportunity to do that in Canvas. Okay. Now let's change gears a little bit and go back to thinking about bars that are being loaded with a force. Now, a lot of you are probably thinking, hey, I'm really glad that in this class we have not thought about distributed forces like we did in statics. Okay, maybe you aren't thinking this, all right? But you're like, oh yeah, that's right, where we had, you know, these just non-concentrated loads of force. We're going to now start looking at distributed forces again. All right, so some of this might be a little bit familiar, and we're at the same time going to connect it to axial deformation in a bar. And for now, I'm going to skip the derivation. So if you want to get the delta, all right, the change in length of a bar, this is the equation you want to have on your formula sheet or on your note sheet. Okay, I'll explain it. All right, and if you want to see the derivation, you can take a look at Hibbler's book, and there's this Professor Rust on YouTube that has done the derivation as well there as well. What are we talking about here? So this is an integral along the length of the bar, and this is a P, it's an internal force, okay? And this is area, which is a cross-sectional, this is the cross-sectional area, A. Okay, this is elastic modulus, and we have a dx, which are these little bits, right? So here's a bar, all right? And let's say it has points A and B on it, and let's say it's the simple case where we have external loads P on the bar on either end, and we're stretching it apart. It has some length L and cross-sectional area A. What is the internal force in this bar? What's the internal force? Yes.
Maybe 2p.
Okay. So
Oh, it's just p.
it's just P, right? So if I break this bar up, right? What am I going to see? I'm going to see that I have a slice, right? And half the bar is gone, right? So, you know, I'm essentially saying, hey, just cut it, right? And then I have an internal force P inside of it, right? Okay, so that's the internal force. It's important to remember that this P right here in this equation is an internal force. Okay, so this one, and it'll come up in I think in a second or so, but that's an internal force. Okay, so now, if we want to think about this displacement, and what we're talking about here is the displacement, essentially what is the change in length of the bar, all right? But if we want to be fancy, we're going to say, hey, what's the displacement between B and A, all right? Or how does B move with respect to A? Okay. Then what we can write out is this fancy equation, okay? And we can, as we said, cut this thing and look at what the internal force is along X. It's nice and constant, and so is A. So this X right here is not P times X, is not A times X, it's actually P as a function of X and A as a function of X. Right? And so what we get here is that we have the integral, okay, of P dx over AE. When I integrate P dx, right, I have P times X. So that might be a little bit confusing, right? But this is because I've integrated that the X's appeared. And now we have an expression where we go from 0 to L, and with PL over EA. This is a big time formula, all right? I call it plea. All right? I plea with you to remember this formula, all right? Some people call it flee, all right? FL over EA. Okay, but this is how you figure out what the displacement is on a given bar. Any questions on this? Now, we have an expression for displacement. We have and it has P in it. And it has some other terms. Where in this course have we talked about a relationship for a bar where we had displacement and we had a force? Yeah, springs, exactly, right? So we can also, think about, that equation, right, for a spring. And we can also think, well, that means that K is equal to the P over delta, which means that, wait a second. K is something related to this L over EA. And there it is, folks. Okay? So remember when I was spitting out those Ks at the beginning and saying, look, just use like 165 kilonewtons per millimeter or something like that. Okay? What was I doing? I was going in and I was saying, well, I know the elastic modulus of steel is 200 gigapascals. I'm giving you a cross-sectional area of A, and I'm telling you it's like 1 meter long or something. And that's how I was calculating out the Ks. So you can remember this equation, all right, if you like, or you can remember this equation, or you should probably remember them both, okay? Because as a mechanical engineer, you'd be like, oh yeah, that's just FL over EA. And now I know how much the bar is extended. Now, if you want to know strain in that bar, you're like, oh, actually, it's just probably easier if I use sigma equals E epsilon. All right, so let's think about what's the stress in the bar, and then we'll say what the elastic modulus is, and then we can figure out epsilon, right? But, you know, you can also do that here, because you could say, oh, I can say delta, I can say, well, delta over L, that's equal to epsilon, right? And I have a P over A, that's equal to stress, right? Right, so, okay, or sorry. So if I do this, right, then I have this epsilon delta, if this is gonna, let's do it this way. This is P over EA, right? And if I have sigma, that's P over A, right? So I can say, well, P over A, that's E, right? So I have, epsilon is equal to sigma over E, right? These are all, they're all under, I'm just manipulating, we're just massaging equations, as some people will say. Okay, yes, Thomas.
This was today's session, Q8, right?
This is number, what's that?
So for session 6, this was question number 8, right?
If you say so, yes. I can't remember. Yes.
Curious,
Yeah. I have trouble remembering all the numbers of the questions. Okay. Good. All right. Let's just make sure, though, that we remember that the P is an internal load, okay? Because we're about to go a little bit further. We're about to say, what happens if we're using an external distributed force, okay? Now, what is an example of, well, that's maybe not a fair leading question. How do I put this? Let's imagine a bar hanging, okay? Or let's just imagine that I've got my pen hanging, right? This is a bar hanging, right? So how much internal force is this, gravity is acting downward, right? How much force is internally at the close to the very tip of this, or this is the, or maybe this is the tip. How much external force, or how much internal force is there over here, near the tip?
MG.
Okay, all right, mg. Let's just say that like I'm using this small piece right here, just like I'm right at the tip. How much internally? It's 0. Okay, there's nothing internal here, right? Because like you said, mg, right? We all think about mg. There's no mass below it to cause it to pull it down, right? Now up at the top, near my fingers, right? What's the internal force? Go ahead. mg, all right? Right? That's because you got the entire mass of this thing, right, being supported up here. So gravity is a great example of an externally applied distributed force. Okay? Well, gravity is really an acceleration, right? But the force is due to gravity, right? Those are distributed. So that makes it kind of a pain when you start thinking about everything around us, right? And it's like, oh man, like I have this distributed load on me just because I'm standing, right? And and gravity is going through me, right? And that also makes sense. Why do you think our head? I don't know. Now I'm getting into stuff that I'm not an evolutionary biologist, okay? But would it make sense to put our brains, or your people's brains, or animals' brains in their feet, where you have this constant force being applied to it? I'm not a neurobiologist, but maybe not, right? So the brain is up here, okay, and I don't have the whole weight of my body on top of my brain. Okay. Anyway, someone should look that up. That was just a thought that came to me right now. I hadn't planned to talk about that. All right. So anyway, what do we have here? This is a little bit confusing to look at. Okay, but the distributed force is getting bigger in this direction. So and it's pushing down this direction, or it's pushing to the right. Okay? And we're going to say that there's a reaction force on the wall, okay? Or let's say this is a wall, and this is some type of distributed force. So this would be like this would be like if we turned this problem sideways, or we rotated it 90 degrees, better said, I guess. This would be like R2 is the force of my fingers now pushing up on this suspended bar, okay? And there's 0 internal force up here, but there's lots of internal force down here.
What's R1?
R1 is just for kicks. We're going to say that's equal to 0.
Oh,
Okay? But very good, all right? I mean, I guess it's not just for kicks, but you could have a system where I have a bar that's got this distributed force, and then I apply another force on top, right? And then I've got both a constant force and a distributed force, right? So maybe it was a little confusing to include that, but it's not there. Okay, so now if we use the CDO approach, where we have an opportunity to look at equilibrium, right, geometry, and constitutive equations, all right, we can attempt to break down this problem. So first, let's look at equilibrium, all right? We can say that there is a balance between this R2, okay, and whatever this kind of overall force acting on the bar might be. Okay. Now, here we are going to try to keep things simple. As we said, we're going to say that R1 is this equal to 0, right? And R2, right, if we want, we can say there's some slope here. There's some constant times the length that's going to be equal to R2, all right? Now, let's break it down into internal equilibrium. All right, and so what we're saying here, this is an internal force, right? And mx is this is So we have some constant, right? And we're moving along here. So if we look at internal equilibrium, okay, this is where things get a little bit interesting. We can say that we have an internal force, right, acting on this system. We have an external P acting on this system, okay, because this is the external P, and we have this R2 acting on the system. So now, if I've defined, and this is a little bit unconventional because usually we define Fi, right, as coming out. Okay, so this is maybe not the bestest, right, but we're going to be very careful and very clear, all right, and when we get down to here, okay, we're going to say that Fi is negative, right, but what we can say is that we have our Fi, our P of x, all right, given by this, which is an external load, and we have our R2, okay, which we defined through equilibrium, okay, as being this ML. Another way to think about this is to say, okay, if I want the P of L, all right, this external thing, right, that's like integrating mx, okay, from 0 to L. Okay, that's the ML that we have. So now we have Fi here. Yes.
I'm confused where like ML came from, and what is that?
Okay, so M, this is a distributed force. Thank you for asking that question. It was Ibrahim, you asked?
Yeah.
Right, okay. So M is the slope, all right, for this distributed force. In other words, we're saying it's a distributed force and it's not constant along here, okay? And so what we're saying is that as we move along, all right, from the top down, that external force, being applied to the system is increasing, right? Because like we said, the weight could be adding up. So this M is a constant, all right, times a distance that gives us this distributed force. Okay, or it gives us the force, at a given location. And it's getting bigger as we go to the right. Okay, does that make sense? Yep, no problem. Okay, so now we've done equilibrium. We know that we have this internal force Fi, and it's related to this distributed force. So you see mx. This is an external distributed force, so mx, right? So that's like minus the p of x here, right? And we have this overall ml, okay, that we integrated. Okay, that's for R2. So we come back to the equation that was defined here, all right, for displacement. And we say, all right, I'm going to plug in my internal force now, Fi. And when I do that and I do the integration, I get the following expression. Okay, so the displacement of this bar, all right, with a given length, okay, is going to be given by minus ml squared over 2EA. Right? It's a little, this example may be a little confusing. We're going to do another example, which is a little bit more classical in nature. All right, in a second. Any other questions on this? Yes, Michael.
A is a constant.
Yes, A is a constant, and I'm glad you pointed that out because it doesn't have to be. It doesn't have to be, all right? It could be changing as a function of x. So if, for example, if it was a conical structure, okay, then A would be changing. The internal force could also be changing with cross-sectional area, okay, as it moves. Okay, now let's look at this more classical example. Okay, let me just erase these so that they're gone for the future. We have a bar now, and that one we said was kind of like a bar being supported on the bottom. Let's talk about a bar that's hanging. Okay? And there are lots of examples of these types of situations where you've got something that's under gravity and it's hanging. It could be a very long cable, for example. and gravity is acting on it. It could be a structure. So what's going on here? Well, if when we do the external equilibrium, okay, this one's a little more intuitive. External equilibrium, we have a reaction force here, and everyone's like, oh, yeah, now I know it's just mg. Okay, that's because that's the total mass of the object times gravity, which is acting on it. Now, what does that mean for the reaction force? Well, it means that it's mg as well. And what is m? M is density times volume. So m is the rho times the length times the area, and g, right? So m is just, and you had some experience on one of the previous problems. I don't remember which number it was, right? But when we were looking at, okay, we're suspending this acrylic sheet, and we got to figure out how much force, right, it's exerting on the two cables. So that's when we said, okay, it's rho times length times area, or rho times volume. Okay. So that part's not too bad. Internal equilibrium. Okay. So now, what are we going to say? We're going to say, can we come up with a relationship between this distributed force, or a distributed force, okay, and an internal force? Because if we go back, our goal here is to figure out what this internal force is as a function of x. And we're going to think of there being a distributed force on this system, and we're going to think of it as being something like a lowercase f. Okay? And so if we have a distributed force, and we say that it's going from a 0 to an x, okay, we can say that we have an integral, right, rho ga dx, and this is what the internal force will end up being. Now, this would be an internal force, right, where we're saying that it's very low, okay, when it's down here, but as it goes up, it gets higher. Okay? And this internal force, okay, or this distributed force, right, can be given as this. If we do internal equilibrium, all right, so this got erased, okay, but if we do internal equilibrium, what we'll see is that we have a internal force P now, okay, a force F from the distributed force, and then the reaction force. All right, so what were we saying here? We're saying that this is the F. What in the... What just happened? Okay, so this is the internal force, or this is the distributed force, okay, and that's an external one, like we talked about. This is the reaction force at the top, from the top. This is the R that you have here. Okay. And so now we can figure out what the internal force is in terms of rho Ga times quantity L minus X. Okay, like here. And then we combine these expressions and we put them into the constitutive equation, and this is what we get as a result. This is kind of the classical response for how much stretch, okay, we're going to have, okay, of a beam that's hanging from a ceiling and acting under gravity.
That's always gonna be the case.
Well, if it's just a beam like this, yeah,
Yeah.
yes, okay, but it could be you could have multiple beams. You could have beam on beam, right? They could have different elastic moduli, right? There are different things that you could find yourself doing.
Does it not matter if A is changing since A is
Ha. So this is independent. Yes, this is independent of the cross-sectional area. Okay, sorry. This is what we're looking for here. This is the free body diagram. It did appear. Okay. Other questions? Yeah, it's because these A's, they cancel out right here. Okay, sorry about that. It skipped some of this stuff. I was going ahead without it. Okay, so you'll get an opportunity to do one of these or multiple of these types of problems, okay, with distributed forces. Here's another one, and this is from a previous exam, okay, where we have a spinning blade, all right, and because of the centrifugal acceleration, and you can think of a centrifugal force, right? You're going to have strain, and you're going to have a distributed force acting on this blade. Where's the force going to be highest? It's going to be highest near the center, right? Because it's supporting all of that mass being flung outward as a spinning. Okay, and there'll be a few questions on that, and that's our session number 7. Any questions? Okay. All right, now we're going to go on to session number 8. Okay, this one will be a little more interesting, maybe. All right, just maybe. Okay, we'll see. Let me go ahead. What I'm going to do is I'm going to close this.
Are both sessions 7 and 8 due tomorrow morning?
They are. Yeah. Yeah. We got a lot. Okay, hold on a sec.